Dalton's Playhouse Part 2. Priestley collected the gas but had no idea what it was. He observed that a candle burned brightly in it, and when he placed a mouse in a container with the gas, it lived normally. Priestley did not fully understand the nature of the gas. He thought that it was air absent of some poisonous substance which he called phlogiston, and that it would snuff out the candle or kill the mouse if phlogiston was present. As a result, he named the gas produced dephlogisticated air, which means air without phlogiston. Others, including Antoine Lavoisier, would carry out additional experiments. So here we'll click Next to continue with Lavoisier's lab. So here is my setup, and I'll point out that I do have my Part 2 lab report over here. Point out a couple of things about what I'm going to ask of you. Is that we have a lot of different types of data present. We have oxygen, phlogiston, and water vapor present. And I'm going to be asking you to record that data in terms of masses and volumes. But that's okay because the data generated here is in terms of masses and volumes for all three substances. Okay. Now, here the only thing that might trip you up is that the product is actually the water vapor. Now, before I get into describing how this apparatus is set up and how you can actually tell that it's a product, water vapor that is, I want to point out how to fully complete this data table here. So this animation is going to take about 12 seconds. And so what I'm asking you to do is fill out all 6 of these data points at the 1/3 mark. Well, 1/3 of 12 is about 4. And so at the 4-second mark, I want you to press pause and take down all of this information. The mass of oxygen, phlogiston, and the product, which is water vapor, as well as the volume of oxygen, volume of phlogiston, and the volume of the product. Again, water vapor. Do the same thing at the 8-second mark, which would be the 2/3 mark, and then fill out the data again for the final analysis at the end. Okay. All right, so we can see this apparatus setup. We have the combustion chamber right here, and I'll tell you that there's going to be a little flame. There's going to be a little burning right here. And if you follow the 2 pipes that are going to be right underneath the flame, and by the way, that's kind of how you know that that's what you are burning, right? That's what the things are actually reacting. And so if we follow this pipe, we can follow it all the way up here and into the oxygen container. So oxygen is going to be pulled through this pipe and then delivered to the flame so it can burn successfully. We can follow the other pipe up and out, and it'll be the phlogiston container. Again, the phlogiston will be pulled through this pipe and into the burning flame and then be consumed. The product, which is water vapor, is in this 3rd vial, and if you follow its pipe, you can see that it is actually coming out right above the flame. And so that's how you can tell that it's the product, because that water vapor is going to be very, very hot. It's going to want to rise. It's going to be pushed up and through that pipe and then collected in this container where it can be measured. All right, so let's let it run. Again, I'm not going to press pause at the 4-second mark and the 8-second mark to take down the data. You'll have to do that, however. And we're almost done. We can definitely see that the oxygen and phlogiston being consumed because there's way less of it now. You can tell that. And we produced a lot of water vapor. Let's run it one more time. You can see that there's a lot of oxygen, and you can see the level of water going up. That's an indicator that there's less and less and less oxygen in the actual container. The idea being the oxygen's being consumed in this combustion. One more time, we can see the same thing happening in the phlogiston container as the burning is occurring, but we also see the opposite happening in the water vapor container. You can see that there's actually water vapor being produced and pushed into this vial where we can then measure it. And so we can visually see that the phlogiston is being consumed as well as the oxygen. We can therefore see the water vapor being produced. Okay, so hopefully you were able to collect the data in your data table, and we can move on to our free response questions. Number 1, with relation to the volumes of the gases, in what specific proportion did oxygen react with the phlogiston? Okay, now you're going to be able to see this in any specific row here in your data table. Even if you're looking at the 1/3 burn, the 2/3 burn, or the all burn, you're going to see the same proportion, right? Because these things are going to be reacting in the same proportions. So, oxygen reacting with phlogiston. Well, let's look at the amount consumed here. So, oxygen, okay, we started with 22.4 liters. We ended with 11.2 liters. So that means that we consumed 11.2 liters. We consumed 11.2 liters. For the phlogiston, we started with 22.4 liters and we ended with nothing. And so that means we used all 22.4 liters. Well, that means we have to use 22.4 liters for every 11.2 liters of oxygen. Well, some simple division shows you that that's a 2-to-1 ratio of phlogiston to oxygen. Okay, so for every 2 volumes of phlogiston consumed, you need to consume 1 volume of oxygen. Okay, so that's the proportion at which phlogiston reacts with oxygen. 2-to-1. Number 2, how did the mass, so here we're talking about mass again, how did the mass of the gas in all 3 vessels before burning, okay, so take the mass, all 3, right? Take the mass, all 3. So again, we started with 0 water vapor, we started with 2.02 grams of phlogiston, and we started with 31.99 grams of oxygen, right? So, we can add that up. How does that mass compare with the total mass after burning? Well, hopefully you're remembering the law of conservation of mass here, and that if we take the starting amount of oxygen, the starting amount of phlogiston, and the starting amount of water vapor, it will be exactly equal to the produced amount of water vapor plus the remaining amount of oxygen. There's no remaining amount of hydrogen or phlogiston because it was all consumed. And so what you should see is if we add 15.99 grams of oxygen remaining to the 18.02 grams of water vapor produced, we should see the law of conservation of mass completely satisfied. And in fact, that's what we see. They're the exact same masses. All right, well, let's complete our multiple choice questions here. See if I can keep the data on the screen. Number 1, observe how the volumes of gas change in the reaction and compare the rate at which the starting gases were used up. How do they compare? Now, we're referring here to our answer to number 1 on the free response questions. A, they were consumed at equal rates. No, we need twice as much phlogiston as oxygen. Oxygen was consumed faster than phlogiston. Well, no, you need twice as much phlogiston. So phlogiston was consumed faster than oxygen. And if you were to run the animation again, we can do that again, you'll actually see the volume of phlogiston go away faster than the volume of oxygen. That's an indicator that you're actually consuming the phlogiston faster, simply put. So you're consuming the phlogiston faster than the oxygen. Number 2, with relation to the volumes of the gases. Okay, so now we're talking about volumes. In what specific proportion did the phlogiston react with oxygen? Well, it was 2 volumes to 1 volume. We need 2 phlogistons for every 1 oxygen. Number 3, how did the mass of the gases in all 3 vessels before burning compare to the total mass after burning? Well, we already answered that in our extended response. The total mass of all materials decreased after reaction occurred? No. There's no decrease there. There was no change in total mass of the materials after the reaction occurred. Sounds good to me, right? I might have clicked that a little prematurely. Make sure that you read all the potential responses in case there might be a little tricky one at the end. But it turns out that B is the correct answer. All right, that does it for part number 2, Lavoisier's lab.